S. Chan presents Educational Video Lectures. Difficult concepts made easy. Study anywhere, anytime.
Welcome to S. Chand Academy, and I am Anmol Bhatia. The course that we are doing is in Applied Thermodynamics, and the topic of this video is second and third law of thermodynamics. In our previous videos, we have seen what is first law of thermodynamics, and we have seen what are the major limitations of first law of thermodynamics and why there was a requirement of second law of thermodynamics.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box.
The topic is second and the third law of thermodynamics. So we have two connected statements with second law of thermodynamics. So those two statements are Clausius statements and Kelvin-Planck statement. Clausius statement in brief states that heat cannot flow from the colder body to the hotter body, and Kelvin-Planck statement states that all the heat cannot be converted into the work. So both the statement collectively is related to second law of thermodynamics. So what happens, this conversion plays a very critical role in certain application areas, and as per the statement of these laws, I am reading it. It says that it is impossible for the self-acting machine that is moving in a cyclic process which is not aided by any external agency, external energy, to convey heat from a body at lower temperature to the body at the higher temperature. And in other words, heat cannot flow from the colder body to the hotter body. And Kelvin-Planck statement says that it is impossible to construct an engine which operates in a cycle that produces no other effect other than extraction of heat from the single reservoir. That means all the heat cannot be converted into the work. This is the second law of thermodynamics collectively. So we have three cases which are associated. Number one, heat engine, then the second is heat pump, and the third one is the refrigerator. So if I look at the first one, heat engine. So heat engine is that particular device that takes the heat from a region which is at a temperature at a higher body, a higher temperature value, and it takes the heat from there, converts that heat into work, and reject that heat into the sink. Sink is that lower temperature region. Whereas heat pump and reservoir are the two categories in which the heat is extracted from a particular region. If it is a refrigerator, then our concentration is there on this T2, because we want to cool this region down. So whenever we want to cool a particular region, we have to extract the heat from that particular region. So the heat is extracted from the region with the help of the compressor. We have to put in certain work into it, and it rejects the heat to the outside environment. This is particularly for the case of refrigerator. Now if I talk about a heat pump is basically a device which is used to heat a particular environment. So our attention will be there on this temperature 1. So we want to get this region which is at a particular temperature T1 heated. So we want to supply more heat into this particular region. So we need to extract the heat from there, supply the heat into this particular region with the help of the compressor. So this is what we called as a heater and an AC concept. So this same concept lies in this particular diagram. Now as far as this heat engine is concerned, I have told you that it takes the heat from this particular reservoir and rejects the heat into the sink. It produces work. So in general, we want to find out what is efficiency. So efficiency here is work over the energy input or the heat input, the output work over the heat input. Efficiency in general terms is the ratio of output to the input. So output is what we are getting. So we are getting this work, and input is what we are supplying. So we are supplying heat Q1 and we are getting this work W. So as far as this energy balance or energy equivalence is concerned, so Q1 equals to W plus Q2. So Q1 minus Q2 will be equal to W. We can substitute that value in this particular expression. So efficiency is Q1 minus Q2 over Q1. So we can divide or solve it by dividing this Q1 with this and this. So we'll get 1 minus Q2 by Q1. That is the particular representation for efficiency calculation in terms of heat engines. Now if the heat pump and the refrigerator is concerned, so we have this expression which is coefficient of performance in case of heat pump and the refrigerator. So coefficient of performance in general aspect is desired effect over work done. In general it has this formula, desired effect over the work done. So you can see the desired effect in case of a refrigerator is to remove the heat from this particular region. So when the heat is removed from that particular region, so our attention is basically focused on this Q2. So Q2 over this work done in case of a refrigerator. So work done is similar, Q1 minus Q2, that is equal to W. As per the energy balance we can substitute. So Q2 will be equal to COP will be equal to Q2 over Q1 minus Q2. Then you have the expression which is for the heat pump. For the heat pump, as I have told you, that our attention is on this region that we want to heat up. So our attention will be on this Q1 part, that is the desired effect for us. So desired effect is Q1 over W. So we can substitute both the values. So we'll get this COP which is Q1 over Q1 minus Q2. So this is basically for the heat pump and this one is for the refrigerator. So when we look at both the expressions, so this can be clubbed up with one general formula, which is COP of this heat pump is equal to COP of refrigerator plus 1. That means they can be mutually convertible. So we can convert this AC into a heater. That is one of the example of that all weather AC, in which sometimes you want to heat that particular environment or sometimes you want to cool that particular environment. So that can be mutually convertible and that can be done with the help of that particular categorizations. So we stop here for a short break. After coming back from the break, we will understand this second law and third law of thermodynamics more in detail.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break. Before going to the break, we have learnt the concept of heat engine, heat pump and the refrigerator, and we have seen the cases of coefficient of performance calculation in case of heat pump and the refrigerator, and additionally we have seen the efficiency calculation in case of a heat engine. Now in this part of the video we will learn about one particular machine which is called as perpetual motion machine of the second kind, that is particularly called as PMM-SK. So a machine that particularly operates in a cycle, and that machine converts all the heat into work. So we have this reservoir which is at a particular temperature and we supply that heat from that particular reservoir into the heat engine that converts the heat to the work, and we get all the heat converted into work. That particular exchange of heat within a single reservoir that particularly is not possible, and that machine is particularly called as perpetual motion machine of the second kind. Perpetual motion machine of the first kind we have already seen in the previous part of the videos. If you haven't watched that particular video, you can visit the playlist of the S. Chand Academy channel. Now we have certain cases and that Carnot engine efficiency calculations. So we have irreversible process like friction, or we have the case of heat transfer through the finite temperature difference, expansion process, or the mixing process. A reversible process is basically also called as a quasi-static process, but this quasi-static process in general may not be a reversible process. So what happens if we want to calculate this efficiency and we are given with the temperature values? Let's say we have this efficiency calculation and we know that the formula is output by input. So output is what we are getting from the system. So work is that thing that we are getting from the system, and input is Q heat that we are supplying to the system. So what happens as per this expression, we can say that this heat, the ratio of these heat values can be converted into the temperature equivalent values. So Q heat by Q at the lower temperature over temperature at the higher region to the temperature at the lower region, the ratio. So we have already derived this, that efficiency is Q heat minus Q higher minus Q lower over the Q higher value. And if we look at the proportional value or the ratio values, that can be converted in this particular sense. That means if we know the value of heat or if we know the value of temperatures, efficiency can be calculated, and that particularly is the baseline to get an expression for this efficiency in terms of temperature. But you need to make sure that these temperatures are in Kelvin particularly. For an example, if let's say you have this Carnot engine which is draws this 500 kilojoules from this environment, and you need to find out how much work it produces. So what we need to do, we need to get this efficiency formula, which is this formula, and the temperatures that we have is with us, like we have T higher minus T lower values 650 and 300. So we need to convert these temperatures into Kelvin and then get a difference. Here you can see that I have not converted it into Kelvin, but as far as the difference is concerned, so when we put in these temperatures in degrees Celsius or in Kelvin, we will get the same value of difference. But for the denominator part, you have to convert it into Kelvin because it is a single term. So on solving, you will get this efficiency. When we multiply this efficiency with the heat drawn that is given in the question, so we can get the work output, because efficiency is equal to work output over the heat input. So heat input is there with us, which is 500, and efficiency is also with us. So efficiency we have 0.671. We'll multiply it with the heat input, which is 500. So we'll get that value, which is W value. So W can be calculated from there. Now we have this categorization of heat pump and refrigerator. As I have told you that this Q1 by Q2 is having an equivalence relationship with the temperatures. So COP for this heat pump and refrigerator can be expressed in terms of temperature also. So T1 over T1 minus T2 and T2 over T1 minus T2 for the case of refrigerator, and the diagram remains the same. So in case you have given in the numerical with the heat or you are given with the temperatures, you can substitute these values to obtain the coefficient of performance for refrigerator and as well as for the heat pump. Now what is entropy and how it is related to this third law of thermodynamics? So entropy has certain definitions. So it is basically the measure of disorder, or you can say for an isolated system and for the universe, entropy will never decrease. And whenever there is an increase in entropy and that increment is very small, so heat is added to the higher temperature, and that greater amount of heat addition is made to lower that particular temperature. Additionally, entropy is a function of energy and the temperature equivalence. So this entropy is also represented as ds equal to delta q over that T. So you have this energy and the temperature equivalence in the same process. Now you have this statement, which is the third law of thermodynamics. The third law of thermodynamics states particularly the entropy of, for all this perfectly crystalline solids, that entropy is 0, and that 0 value is there for the absolute 0 temperature. Absolute 0 temperature is 0 Kelvin. That means minus 273 degrees Celsius is that particular temperature at which the perfectly crystalline solid will have the entropy. That means the degree of randomness as 0. And this particularly is the baseline in which that provides a calculation for the absolute entropy for the substances, and the entropy is particularly 0 for that particular temperature, which is 0. So for pure substances, it states that this entropy is 0 at that absolute temperature, and that absolute entropy value is helpful in the calculations in the forthcoming applications which are related to ceasing of that particular process. Now lastly, we have certain deviations, certain differences between the two systems. One is homogeneous system and another is the heterogeneous system. So as the name suggests, homogeneous is only related to the single phase, a system that consists of a single phase, let's say a mixture of air and water, or you can say the water with nitric acid or the octane plus heptane. That means it only has a single phase associated. But heterogeneous systems are the combinations in which it consists of two or more phases. Let's say air and water is there, and another example is this same thing, but you have different phases altogether. So you have two different phases in this particular category, and you have the same phase. Those systems are there in the same phase, that particularly is called as a homogeneous system. Now lastly, you have this adiabatic system in which the heat remains constant. That means a categorization in which the system becomes isolated and no heat can leave that particular surrounding. That is particularly the categorization of adiabatic system. Now you have point functions and path functions. So point functions are basically those functions that depends upon the particular characteristics, and path functions depend basically on the path that is there to achieve those particular states. Examples, you have this internal energy, enthalpy, all are these point functions, and these are denoted by the case which is that D, and that path function are the dependent cases which are particularly dependent on a particular path, and we have seen that categorization with the help of that examples in the previous derivations. Additionally, we have a case of a steady flow process. So in many practical problems, the rate at which the fluid flows through the machine or piece of apparatus is constant. That is particularly related to the steady flow process. A steady flow process is that particular process in which the rate of fluid that flows through a particular machine is basically constant. So the flow is particularly constant. We have certain assumptions that are required to be followed in case of the steady flow system, like mass that we are considering is constant, the fluid flow is uniform in that particular composition, and the only interaction between the system and the surroundings are heat and work. And if we talk about that the fluid at a particular point, that fluid remains constant with the time, and during analysis only the potential kinetic energy and the flow are to be considered. For that particular situation, the steady flow processes are valid. So what we have understood certain applications of the second law of thermodynamics in terms of refrigerator and heat pump, and we have seen some derivations which are related to heat engines, and additionally we have seen some terms like homogeneous systems and the steady flow processes. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission